work that I've been doing with Marco Baggio and Kyriakos Papadodimas, recent work that has appeared in these papers, but also I would like to report some new, surprising, we think, observations that we hope will appear soon. So I'm going to talk about correlation functions in four-dimensional n equals 2 superconformal field theories. The approach I'm going to take is slightly orthogonal to many of the things we've heard so far. So I'm not going to make any approximations. For example, I'm not going to take any large MCV. I'm not going to make any approximations, but there is a compromise I will have to make. I will consider a restricted class of observables. However, this restricted class of observables, we'll see, is quite non-trivial, okay, and relatively less explored, not very much explored. Okay, so we're in 4 dimensions with n equals 2 supersymmetry, so we have 8 real supercharges. And I'm going to consider a situation where we have continuous families of n equals 2 superconformal field theories. And usually when we have such situations, it is useful to think in terms of an n equals 2 superconformal manifold, which is a space parameterized by the n equals 2 exactly marginal couplings. Okay, so it's similar to, say, n equals 4 Sperry Mills, where we have an exactly marginal coupling, and we can tune freely that exactly marginal coupling. So as we vary the exactly marginal couplings and move across the space, the generic properties of this theory change. Okay? So the spectrum of a generic operator, correlation functions, etc. And ideally what we would like to be able to solve is to find the exact coupling constant dependence of generic observable. Clearly this is a hard question because it's a non-perturbative question. So my compromise, as I said, is I will try to solve this problem in a for a restricted class of observables. So I will focus on the usual suspects, which are half-BPS operators. There are several half-BPS operators in n equals 2 theory, so I will talk about a specific class. And I'm going to consider correlation functions of these operators. So as we will see, these operators are rather non-trivial. They depend non-trivially on the coupling constants, exactly marginal coupling constants, which is unlike a similar situation in n equals 4 Sperry Mills, where they are, in fact, trivial. They are determined, say, at 3 level. There's also a rich geometric structure underlying many of the properties of these local half-BPS operators that will be useful in the treatment of the relevant physics. And we will also see that although they are non-trivial, these correlation functions, they seem to be largely computable. Okay? So here are the operators that I want to consider. We have n equals 2 supersymmetry, so it's an immediate thing that we usually do is to look for physics on the n equals 2 chiral rings. 4-dimensional n equals 2 superconformal field theories have this R symmetry, SU2 times U1. And the operators that I want to consider have the following properties. They are superconformal primaries. They are neutral under the SU2, and they are half-BPS in the sense that they are annihilated by the half set of real supercharges. So they are annihilated by the Q bars, the 4 Q bars, but we can act on them with with the Qs, okay, with the 4 Qs. There's also a complex conjugate version of these operators, the antichiral operators, where essentially the opposite is happening. They are annihilated by the 4 Qs, and these are called antichiral. So as you know very well, these belong in short multiplets. They saturate this bound. So the chiral primary operators, their scaling dimension is equal to the U1 R charge over 2. And that takes care of the spectrum of these operators. So in generic situations, as we vary the exactly marginal couplings, this relation holds. There's no normalization of the R charge. And therefore, we fix once and for all the scaling dimension. Okay? So this is something trivial in this datum of these operators. So what else can we compute? Well, first of all, since they are half-BPS operators, they form a chiral ring, as we know very well, also from 2-dimensional n equals 2 theories. They form a chiral ring under the operator product expansion. So as you bring two of these operators close together, there is no space-time singularity here, and you get some coefficients, which are the OPE coefficients. So you can compute 2-point functions for where you have a chiral and antichiral operator. Space-time dependence completely fixed by conformal symmetry, and you want to determine this coefficient, Gij bar. You can also compute 3-point functions, etc., etc. So on a superconformal manifold, these 2- and 3-point function coefficients, which will be the main target of our study, are non-trivial functions of the marginal coupling constants. Okay? Now, n equals 4 is a special case of n equals 2, and it has more symmetry. And precisely in this case, there are, because of the extra symmetry, there are special non-renormalization theorems that tell you that, in fact, these quantities they are trivial. They do not depend on the coupling constant. Okay? So in that particular case for my purposes would be a trivial one. Everything is determined essentially by weak contractions at tree level. Okay? It would be a group theory statement, as was noticed already back in '98 by Siraj, Rangamani, Zyberg, and elaborated further by various people. Now, one thing, so suppose that you solve the problem and you know the exact coupling constant dependence of these coefficients. What else do you buy? And you can use superconformal word identities to argue that once you know this, basically you know all the extremal endpoint functions of this form where you have a single antichiral insertion. Okay? So this is essentially the set of data that we'll try to attack. Now, there are two geometrical properties that I want to summarize that will be quite helpful in thinking about this problem. First of all, I talked about exactly marginal deformations that preserve the n equals 2 supersymmetry. It turns out that the form of these deformations is quite restricted. It's essentially of F term type. So the couplings naturally come in complex and their complex conjugate pairs. So I will call them lambda I and lambda bar I. And the interactions here are descendants of precisely the n equals 2 chiral primaries that I mentioned. In fact, you need to have special chiral primaries with scaling dimension 2. So scaling dimension 2 plus 2 from the Q's gives you something that has exact scaling dimension 4. And therefore you get an exactly marginal deformation. So in what follows, I will reserve these small Latin letters precisely for this chiral and antichiral primary fields with the special scaling dimension 2. Okay. Now, as we know from Zomolodchikov, when you have a conformal manifold, you can use the exactly marginal interactions, operators, to define a natural metric on this manifold. This is called the Zomolodchikov metric. In this particular case, the only 2-point function that is non-zero is one between a holomorphic O and an anti-holomorphic O. So you get these quantities, and that defines a natural Hermitian metric on the superconformal manifold. In fact, with n equals 2 supersymmetry, it turns out that this metric is a complex scalar manifold. In other words, Gij bar is given in terms of two derivatives of a scalar function, the scalar potential. Now, one of the recent developments in recent months is a theorem that was put forward and proved by these people, Gerskovits, Gomis, and Komargotsky, and further elaborated by Jaume, and was followed up on previous work, similar statement of this type that was made in 2 dimensions by other people, that states that the exact quantum Keller potential on the superconformal manifold is essentially given by the logarithm of the S4 partition function of the theory. Okay? So everything I will be computing here are quantities for the flat space theory, but this theorem states that this flat space quantity is directly related to the S4 partition function. And for many theories, we know exactly how to compute that S4 partition function. As we know from Pestoun's work, the sphere partition function can be computed exactly using supersymmetric localization. So this will be one of the tools that I will be using to get exact answers. So already this statement, so let's see. So the Zomolodchikov metric is this quantity, this 2-point function, and these O's are descendants of the phi's. Okay? So you can use a further superconformal word identity to relate the 2-point functions of the chiral primary operators with scaling dimension 2 to the Zomolodchikov metric, and through this to the S4 partition function. And that already is a partial answer to our problem. It determines a part of the Gij bar coefficients that we want to determine. Okay, so this was geometry part 1. There's another thing that I want to mention that will be very useful. Now, it turns out that here we have a non-trivial manifold, the superconformal manifold, And as we change the theory, move on the superconformal manifold, there are operators on top of each point that we want to consider, and their normalization can change. There can be non-trivial mixing, etc. So when you think more seriously about operator mixing and quantum normalization, it turns out that the right way to think about chiral primaries is as sections of vector bundles labeled by the scaling dimension or R charge of these operators. And these vector bundles have a non-trivial connection. Okay? So this non-trivial connection, we'll see in a moment how non-trivial it is, but what this connection captures, for example, is the following. So suppose that, so here is my vector bundle. Basically, choosing a section means that I choose specific conventions, normalization conventions for my operators. And I could go around in the superconformal manifold in a small loop, and just like in differential geometry, I don't have to return back to the same frame. Okay, there could be a non-trivial holonomy, and the gauge connection is capturing this. So one of the things that you would like to compute immediately, just like in curved manifolds, differential geometry, is the curvature of these vector bundles. Okay, and what we've learned already in 2 dimensions by the seminal work of Cecot in Vafa in 91 is that there is a very efficient way to compute this curvature. In particular, what Cecot and Vafa did in 91 is to use topological and topological fusion to determine the coefficient, the components of the curvature. And the resulting equations are called the TT star equations. So precisely this problem was revisited in 2009 by Niarchos, who rederived exactly the same equations in terms of, using superconformal word identities in conformal perturbation theory. Now, what we learned from this game is that, first of all, holomorphic, and non-holomorphic components are 0, so these are holomorphic vector bundles. And then we also learned that we can compute exactly the holomorphic and the holomorphic piece in terms of the OPE coefficients and 2-point functions. Okay, so this is a nice covariant formalism that we can use to describe the superconformal manifold with the vector bundles. But when we work with specific contexts, it is more practical to select a particular scheme and convert the TT star equations to partial differential equations for 2- and 3-point functions. So a convenient choice is to go to the so-called holomorphic gauge, where these components of the gauge connection are 0. Then you find out that all the remaining components of the gauge connection can be expressed in terms of 2-point function coefficients, and that converts basically these equations here into systems of partial differential equations of this form. Okay? So I've summarized them here in this particular set of conventions. There are other superconformal word identities that you can use to prove this statement. Also, this statement that tells you that the C, I, J, K, the OPE coefficients are holomorphic functions of the lambdas. So here is a list of the main questions for this project. So we know we have the same equations in 2-dimensional 2,2 theories. And there it turns out in many examples that this is a very restrictive set of equations where the solution is almost unique. Basically, you give me unitarity, you require unitarity, you give me a few perturbative data, and I get the full answer. Now, it turns out that in 4 dimensions, things are not so restrictive. So first of all, you can ask how restrictive are these equations. They're clearly a non-trivial set of constraints between the different 2- and 3-point functions. Is there a recognizable integrable structure in these equations? Can we use this integrable structure to find a complete solution in terms of a few data? Okay, so here, in order to try to understand these questions, it is a good idea to start first with a simple example where we can have something concrete, and we try to understand what happens. So here's the canonical example that I would like to consider. It's n equals 2 superconformal QCD theory. It's n equals 2 Sperry-Mills theory, and from now on I will be very explicit. So we have gauge group SUN coupled to 2n hypermultiplets, which is a well-known superconformal field theory. The n equals to chiral ring operators that I was talking about here have a very specific form. Phi is the complex scalar in the adjoint representation in the n equals to vector multiplet. Basically, the n equals to chiral ring operators are single trace operators that I can build out of powers of phi, and all their multi-trace products. Okay, this is the n equals to chiral ring here. Now, notice that there is a single operator with scaling dimension 2, trace phi squared, And for that reason, I have a complex one-dimensional conformal manifold. So there is just like in n equals 4 per Young means, there is a single exactly marginal direction. And you can check in the Lagrangian formulation of this theory that the corresponding coupling is the complexified gauge coupling, just like in n equals 4 per Young theory. Okay, so our task now is to see how the TT star equations look like in these theories. Let's start from the simplest possible case to see how it works. And the simplest possible case is the case of the SU2 gauge group. So this is simple because we have one chiral ring generator, okay, trace 5 squared. There are no degeneracies, so as I go up in scaling dimension, that's a single operator every time. And the chiral primary, the full set of chiral primary operators are, I will call them phi to n. They have scaling dimension to n, and they're these multi-trace operators in general. So I'm going to normalize them in a slightly unfamiliar way. Instead of normalizing the 2-point functions to be 1 and then working out the 3-point functions, here I'll do the following. I will normalize phi 2 by normalizing the exactly marginal interaction in the Lagrangian in a very specific way and having a specific normalization in mind for the Qs. That tells me how to normalize phi 2. Once I have the normalization of phi 2, basically I will normalize all the other multi-trace operators so that the OPE coefficient is 1. Okay? So I take phi 2 with phi 2, and that will give me phi 4, and I normalize phi 4 so that the C here is 1. Okay, so and this is a consistent choice with the holomorphic gauge because we saw that in the holomorphic gauge, these quantities have to be holomorphic functions. Okay? So here they are constant. Okay, so the remaining task is to find these coefficients, the 2-point function coefficients. When I solve for this, I know the 2-point functions, the 3-point functions, all the extremal n-point functions in the n equals 2 chiral ring. The same precise quantities I will also encounter in n equals 4, in the half-BPS sector of n equals 4, and there the answer will be trivial. It will be completely determined by doing weight contractions. It would be a group theory exercise. Here it's highly non-trivial, as we will see. So here is the form of the TT star equations. They become like this. And you see, G0 by definition is 1, so if you give me G2, you see here G2 and G0 will appear, and from this one I will get G4. You give me G2 and G4, I will give you G6. So it's a recursive equation, and basically if you give me one member, I know everything. So in fact, it's a rather famous chain. It's a semi-infinite Toda chain that has also appeared in examples of TT star equations in 2 dimensions. And you can easily see that by doing this filter definition. So that's the take-home lesson. One datum is G2, which is essentially the homologic of metric, and you can determine from localization, determines everything. So it's now nice to go back, use the, basically for the SU2 theory, the S4 partition function is given in terms of a one-dimensional integral, do a perturbation expansion of that at weight coupling, then you get very specific numbers for the expansion to low orders, the 0 instanton sector, 1 instanton sector, etc., for all these correlation functions. In fact, we went ahead and did a 3-loop computation to check that everything is reproduced in perturbation theory exactly, and that all our conventions are correctly implemented. So that's the SU2 case. And it's a rather trivial case in a sense because there wasn't much structure to play with. Everything was automatically fixed. So the place where we really hope to learn something new is the general SUN case. Now, this is a more complicated and challenging case where, and this is so because we have more chiral ring generators, as I said in the beginning. So we have non-trivial degeneracies. As you go up in scaling dimension, more and more operators with the same scaling dimension appear, and the size of the matrix of the 2-point function coefficients grows indefinitely. Okay? So again, if you choose conventions where the OPE coefficients are 1, the TT star equations take this form. Okay? So it's a complicated set of partial differential equations for matrix-valued quantities. You see, I also have to invert these matrices here. I have to take traces. I have to also, you see, just like in the SU2 case, I have 2-point functions for chiral primaries in 3 different scaling dimensions. And the way I go from one scaling dimension to the other is multiplying by phi to trace phi squared. Okay, so trace phi squared here plays a prominent role. So the question, our task is really, can we find any solutions to this? Okay? what external data, like the Zamolodchikov metric, will we need here to solve this completely? It's not clear. This is not recursive, automatically recursive, like in the SU2 case. So here I would like to offer a preliminary observation that it seems to really be verified by concrete computations, and we find very surprising. I mean, it didn't have to work, and for some time we thought that it shouldn't work. Okay, so let's assume that there is a constant linear. So first of all, here all these equations are written in a specific set of conventions, as I said, the holomorphic gates. Okay, so let's suppose that there is a constant linear transformation with elements m that do not depend on tau and tau bar, where I go from the phi else to the phi prime to a new basis. Okay, and this linear transformation has the following properties. First of all, it diagonalizes GKL bar, all the 2-point function coefficients, and secondly, it keeps the OPE between phi 2 and phi prime k in this form. So only one chiral primary appears on the right-hand side. Okay, so this was the form of the OPE that we had in the unprimed basis. Okay, now if you accept this, okay, and I will discuss whether this is viable. Okay, if you accept this, then you can show that the T star equations reduce to a decoupled sequence of Toda chains, of the same Toda chains that we had before. Okay, they become again recursive. Okay, they become again recursive, and again you give me in its orbit you give me one member, and I compute everything else. Okay, now, is this transformation viable? Why is it a peculiar transformation? Because these are supposed to be tau and tau bar independent quantities, but these quantities already are highly dependent on tau and tau bar. Okay, and the M has to diagonalize that. So, such a transformation requires highly non-trivial properties. In particular, all the GKL bars have to obey additional specific properties that will allow this diagonalization. Okay, I will call these relations, and I will give explicit examples in a moment, horizontal relations. Now, once you have this property, the gates connection in the prime basis will be reducible. So, if you have chiral primaries at any scaling dimension delta with degeneracy D, you would expect that as you go around in a loop in the superconformal manifold, the holonomy will be U of D. Okay, everything would mix. But it turns out with this ansatz that the holonomy is reduced. It's U1 to the D. And this is related to the fact that if we go in the prime basis, so we have everything orthogonal in, say, a tree level, we do quantum corrections, and there is no mixing induced by quantum corrections. So that looks like a non-renormalization theorem. So also this OPE here, because everything is at tree level, everything is tau and tau bar independent, this implies, requires group theoretical identities all exactly at tree level. So these are, there are some mathematical identities about group theory quantities here that are required for this. I will call these vertical relations. So let me give an example of this, how they look like. So suppose that we do a rotation that takes, basically doesn't touch this operator. So you go from this operator to this operator again, okay? But you basically decouple it from all the other degenerate chiral primaries. Now, for the horizontal relations in this case, I will require this ratio of 2-point functions in the original basis not to renormalize. Okay, that will be my non-renormalization theorem here. The requirement will be that this is a tree-level quantity. Okay, you see trace phi squared to the n with any degenerate operator over the 2-point function of trace phi squared to the n with itself, which it looks like a very surprising thing to require. Then, for vertical relations, what you will need, these are called vertical because they relate 2-point functions at different scaling dimensions. So you will require that this quantity is equal to this quantity. This quantity is basically this one where I have multiplied everything with a trace phi squared. So you trace phi squared to the n plus 1, phi bar with trace phi bar squared, etc. Okay? And you should check that these quantities are the same since they do not depend on tau and tau bar. This is a tree-level identity. Okay? So it turns out we have now a general 3-loop formula for all these 2-point functions. And we have checked a lot of examples, and in all examples, these identities are verified. Okay? For example, let me give you an example. So in the SU4 case, we have the generators are trace phi squared. I'm almost done. Trace phi squared, trace phi to the cube, trace phi to the fourth. At delta equals 6, we have these 3 degenerate operators. We have a 3 by 3 matrix of 2-point functions. We computed a 3 loop up to the order g to the 4th. And basically, the horizontal relation here translate to specific relations between all these coefficients. In particular, they relate to the identity that the product of this number times this number is the same as the product of this number with this number. And you can check it works. Okay? And there are many, many examples like this that always work. And we also have preliminary evidence for the full decoupling, not just for this case. So one of the consequences here is that in the general SUM theory, if you consider again these operators that are also considered in the SU2 case, now they obey this standard order chain. So you give me the homologic of metric, the SU n S4 partition function, and I tell you about all these 2-point functions immediately, just like in the SU2 case. And then the horizontal and vertical relations fix many more mixed correlators. This is, I'm done. So just 1 second. So there are many obvious questions here that one can further explore, and I will let you read them. Okay, thank you.
All right, Massimo? Can you wait for the mic?
Where?
The formula that you require, the one where, because these look like extremal correlator, the ones that you want to impose go back no, further.
In front or?
No, towards the end. The condition that this, okay, this one.
Okay.
The numerator of that is a extremal.
Yeah.
So an extremal correlator in n equal 4, for instance, are not renormalized.
Exactly.
So you're requiring that these are not renormalized also in this theory, or?
Right. So here in n equals 2, I don't know of any non-renormalization theorems, and I didn't expect any. I mean, you can see also from direct computation that everything gets corrections. So that seems to be a new non-renormalization theorem. I don't know for the moment, exactly where it comes from. We have some ideas, but I wouldn't like to.
And the next one is what is called next to extremal, isn't it? The numerator in the second relation. Yeah.
No, it's again extremal. It's just different chiral primary operators.
Oh, because it's important.
So you mentioned that the metric on the conformal manifold is scalar. That's already true in n equals 1.
Right.
So one would expect that with n equals 2 you have additional conditions.
Exactly.
What are they?
Okay, good. This is an excellent question. It's in fact something that we're thinking about. So in the two-dimensional story by Qumran, we know that, for example, when C equals 3, we get special geometry because we have additional structure. For example, we have a holomorphic symmetric 3-form. Very much related to that is also, that you have the TT star equations there, and they tell you about the special geometry. Now, if you go at the more generic values of C, there is a more generalized story. Now, it's not obviously like this in this case, because, for example, the chiral ring is not bound from above, just like in 2 dimensions, and that was crucial in 2-dimensional story. So at the moment, it's not clear, although you have the TT star equations exactly, again, in the same form as in 2 dimensions, it's not clear at the moment if there is a generalized special geometry. But we suspect that there is indeed something more special than just Keller. It's just an open problem to get it.
Are there any more questions?
As a holographic dual.
This one doesn't have a holographic dual, but you can take a Z2 orbifold of right, which looks very similar, and that has a holographic dual. You can do the same story.
Theory that should be regulated theory.
Right. So there you can take. Right. Exactly. So you can try to play this game also. Yeah, exactly.
All right. Let's thank the speaker. While we're setting up for the next